Thank you, everybody, for sticking it out and coming to the last of the series this quarter. So it's wonderful to have Dr. Aditya Khuller here. He is a senior research scientist at the Polar Science Center within the Applied Physics Lab at UW. His research interests include studying planetary ices, surface processes, and atmospheres using a combination of numerical modeling, remote sensing data, and he covers pretty much everything from the visible through to microwave, as well as geological mapping. He also has experience with NASA flight hardware development and testing for thermal infrared instruments, CubeSat, electric propulsion, and mission operations software. So today, Aditya is going to talk to us about the evolution of snow and ice on Earth and Mars, and the implications for photosynthesis and the social life within ice on Mars. So please tell us about your research.
Yeah, okay.
Is it on your end or I can't?
I'm recording on my computer, but yeah, you just have to hit OK on yours.
So I don't see that
Oh, it's probably,
on my screen at all.
do you have it on extended screen?
Extended screen. No. It's mirroring. Oh, that's what you meant by it.
Yeah. There you go. There you go from there. Just click OK.
Oh,
The mouse is up there.
okay. Thank you.
Yeah, and then click on your presentation again.
Yeah.
Okay, yeah.
Yeah, that is, okay, awesome, thank you. Yeah, thanks so much, and quick introduction, I joined UW 6 months approximately in October, and I do a bunch of things like Vicky kindly mentioned. Here's astrobiology. Something's off with the colors, like everything's very dark, so hopefully you can see things later on. And then I do other stuff as well. Yeah, I'd moved from LA. And yeah, do a bunch of things. But okay, so the topic at hand, Mars. Mars is similar but also dissimilar to the Earth. Obviously the atmosphere is very different. The pressure is much lower, about 1% of the Earth. It's mainly CO2 gas. The amount of water in the air is very less, 0.1%. And then no known inhabitants, humans. There are 2 robots. This is an image from the Viking lander. And you may notice all the images you see these days from the rovers is everything's flat and boring. This is not. And that's because they landed without knowing where they were going to land, per se. They were orbiting and said, oh, let's land there. And it's a very hazardous location that would not be selected today. The white stuff you might be able to discern on top that looks yellow for some reason is like frost, where the amount of water in the air is actually condensing or freezing onto the surface.
Wait, could you point that out?
Yeah.
So I know.
So all this white stuff, that's also yellow.
Oh, okay.
Yeah, it should look white, but it looks yellow.
So there's a lot.
Yes, lots of water frost. And in places that gas in the atmosphere, CO2 can also condense and form CO2 frost. Okay, but Mars has a lot of ice, and here we're talking about water ice, nothing different from an ice cube that you see on Earth. The phase is the same and everything. Yeah, okay, so these are false color images that have been further falsified. This bluish stuff is ice, and this is a steep cliff, kind of like cliffs you might see in Alaska, where there's ice exposed. And here's the flat surface. Notice about 50 meters, half the size of a football field. And then because Mars's atmosphere is really thin, things are constantly crashing into the surface and excavating the ice below the surface, because the third of Mars actually has ice below the surface. That's an impact crater that's exposed ice. And then in one place on Mars in about 2008, the Phoenix lander actually landed at sort of Canadian latitude, 68 degrees north, and dug 5 centimeters below the surface and exposed ice in this little trench. So we've seen ice in situ at one location. Why is ice important? Yep.
In that first image on the left there, what is what orientation am I looking at? Is this top down or from the side?
It's like if that's a cliff, imagine that's a cliff, this wall, this blue band, this notice board, that blue band is ice in front of you.
Okay, that makes sense.
Yeah.
Thank you.
And then this is actually the top, so the roof of the building or whatever's on top. So we're seeing it like that.
Okay, thanks.
Yeah, why is that important? Just like on Earth, it shaped the landscape, we think, in terms of channels, these things called gullies, and maybe valleys, things like that. So resource of fuel and water. If it's melting, it might host life, hence astrobiology. And then ice cores hold climate records, so you can, here's a example from Antarctica. And is there a way to adjust the color profile of this projector? Like, do you have a remote?
I have never done that before.
Okay. I don't know if there's anything I can do. But okay, anyway. So yeah, here, this blackened core is actually, yeah, literally an ice core where you can examine different layers, because in geology history, it's recorded in layers. And you can analyze the gases and also sediments that are in there. So here's another one of those cliffs. Where here's the flat surface on top, here's ice, and it's hard to discern here, but they're actually layers that you might be able to discern of ice and dust. So we think they're sort of sequential. But okay, so how did it get there? So it turns out, we think just like Earth had ice ages, Mars also had ice ages, but they were way more extreme. And why do we have ice ages on the Earth? We think that the sun is basically pulling us from one direction, Jupiter is pulling us from the other direction. That's causing us to oscillate slightly, but we also have a moon to stabilize us. So the oscillations aren't as extreme as on Mars, where Mars is being pulled by Jupiter and the sun, but then its moons are very small and feeble, so it actually oscillates widely. So it goes from a tilt of as low as 15 degrees to as high as 45 degrees. On Earth, currently we're about 23, Mars is currently 25. And on Earth, when an ice age happens, it's like a degree. Here it's oscillating from 15 to 45. So what's happening is when you tilt up a lot, when the obliquity is high, if there's ice at the poles, sunlight's hitting it, and it's essentially turning into gas, sublimating. And then where it's colder is where there's less sunlight in the mid-latitudes. And so you have water ice being transported from the poles to the mid-latitudes, and then vice versa. When you're low obliquity ice at the mid-latitudes is getting heated up, causing ice to be transported back to the poles. So that's how we think ice got to all these places on Mars. And then today, we're going to talk about this ice we're seeing in these gullies. So what is a gully? So on the left, and yeah, thank you for putting the blinds down. There are gullies in Canada, close to us. And so here's wall rock, a channel cut into the wall rock from snow melting. There's the snow. And then right on the right, there's a very similar looking gully where these channels cut into the rock. And question is, where's the snow? So where's the snow on Mars? So for the last 2 decades, we've got lucky. We've had a military camera, former military camera, flown to Mars that can see things the size of this table. The resolution is 25 centimeters a pixel, way better than any Earth publicly available camera. The military probably can see things like your hair, but we don't have access to that. But as a result, we've got all these brilliant images from high rise. So here's a valley wall from Mars. And you might notice these lobe-like features pasted on to the slope. So they're on top of the slope. And people call them the mantle because they covered the slope. And they noticed they were only on pole-facing slopes, polewards of 30 degrees latitude. People thought they had ice inside of them. And often there are these gullies, like the black arrow is pointing out, that are eroded into the mantle. But before 2021, no one had actually ever seen the ice inside these things. And so today we're going to expose the secret. Okay, so here's actually that same area zoomed out. So this is a valley on Mars in the southern hemisphere, 33 south. And those lobe-like things are all along that pole-facing wall. And you may be able to discern these faint sort of lines that seem to emanate from the slope. And so we joke they're a Martian ski slope. Or let's take a closer look. So now we have that better camera, we can zoom into one of those. And so here you have those gullies or channels cut into the rock. And then over the right, there's another gully cut into the mantle. And right within the mantle, there's ice. Ice exposed at the surface on this steep slope. And we've seen many examples of this. And the way we think about it is, if you look at this mantle, almost like a pizza slice, you can imagine that pizza slice over here. And when patches get exposed, it's covered by dust and debris at the surface, except for over there where it's exposed. When it gets exposed, if it can melt, then it can carve a channel first in the ice itself. If any liquid gets to the bottom, it can then carve the rock underneath. And then when all the ice is gone, you see something like this. So that's the idea. And we've seen this at lots of places. Here's another interesting example. It's a triple crater. So three things hit the surface at once, which is pretty cool. And then on the pole facing slope, we see the mango. There's less of it here, and there's almost none of it on that wall, which is maybe highlights microclimates. Why do you have accumulation on one wall of snow that's then become a buried? So these are basically buried glaciers. If you've been to Emmons Glacier and Mount Rainier, it's like that. So you can zoom in, there's the mantle again, on top of the rock, there are gullies. Zoom in further. Now you can discern the sort of mottled texture as the glacier is essentially flowed down. There's ice exposed, only within the mantle or the buried glacier, obviously. If we zoom in further into just one of these, there's the rock underneath. Here's the scale, 50 meters. And then there's the ice exposed on these steep slopes as the overlying material slumps down. And on the right, you might be able to discern sort of these scale-like features. And we see them in the Arctic, where there's ice below the surface. As the sun heats up the surface and cools down, the ice below is actually expanding and contracting, causing the ground above it to fracture. So this is another indicator that there's ice below the surface, which we now see exposed on the pole on the other slope. And so these are false color images. We've seen a lot of these. I'm on the PhD committee of a student at Arizona State, which is where I did my PhD, for Sarah Bronish, who's actually mapping these exposures of ice throughout the mid-latitude to Mars. She's already found 300. So there's a lot of them. They have a small amount of dust, which we'll get into, how we know that. And one of the places, the first place I showed you, is very interesting because it's at 33 South, which is the closest detection of water ice near the equator, and which is good if you're trying to go to Mars, because there's more sunlight, it's also warmer as you get closer and closer to the equator. And then we got lucky. So in 2009 was the first image. We requested another image, and in 2020 they took a second image of the same spot in very similar lighting conditions. And we noticed a bunch of changes. Normally in geology, things take thousands of years. This is happening today, so it's pretty exciting. We're in America, so I wanted to put a football field and zoom in. So that's the size of the scale of what's happening. It seems like the ice is disappearing. The black arrow is actually showing a channel that wasn't there, that formed. And then the question on top is, what's happening to the ice? Is it melting? Let's see. So can ice on Mars melt? So to do that, everyone brings up the phase diagram, which is this equilibrium diagram. Things can be out of equilibrium, but we're looking under equilibrium. And the axes are the temperature and how much water there is. Normally just as pressure, but it's about how much of that particular substance it's for a pure system. Okay, so this comes from my PhD defense 2 years ago, where in Arizona, where it was 58 Fahrenheit or 287 Kelvin. The humidity was something like 40%. And so if you had ice on the table, stable, how much water would you need in the air? That's what we're trying to get at. So this is the amount of vapor at 100% humidity. At 287 Kelvin, you would need 16 millibars. But remember, we were at 40-something% humidity. So multiply that, you get 6-something millibars. And so what this means is if you take an ice cube out, put it on the table, keep heating it up in equilibrium, it will turn into liquid. You keep heating it up, it'll turn into gas. That's consistent with what we see. Arizona is pretty dry. Here it would happen slower, it would evaporate slower. In Florida, even slower. On Mars, though, it's very dry. So the amount of water is very, very less, just in the air. So there, if you take out ice, the stable configuration is to turn into gas. It would just sublimate. And so based on this, there's this sort of famous paper by Andy Ingersoll at Caltech from 1970. The key point being, when you evaporate, like we evaporate to cool down, and it takes energy. And so basically his point was that there's not enough energy from the sun to actually heat up ice for it to get to the melting temperature, because there's so much energy you'd lose on the way. to just cool down. And so basically you could never melt ice on Mars. So can ice on Mars melt? I guess not, right? But what if it's melting below the surface? So below the surface, if there's any air, it's saturated, it's at 100% humidity. And so you could have liquid water stable below the surface if it's melting there. And so there again, yeah, at the melting temperature, if you're saturated, you have stable liquid water. So now we have to see if there's actually enough energy to do that. And so, yeah, sort of simplified energy balance diagram. There's a bunch of heat from the core, very little conduction when you touch something hot. Then there's solar radiation, which actually goes into the ice. Ice is translucent. And then there's air from or brought by turbulence in the air. And then we all are emitting in the thermal infrared at our temperature. If the snake was here, I'd be happy to see us. Yeah, but on Mars, the biggest two are radiation and turbulence in terms of contributions to energy balance. And of course, people have done this before. They've looked at these things, but there's some limitations with these two key factors. So for solar radiation, the two key factors are dust and how big the snow grains are, which I'll show you can lead to 10 times more heating. Problem is current Martian ice models actually ignore these really important factors, finding no melting occurring, except for two. And they find, by partially including these factors, that you can actually melt ice and have liquid water on Mars today. On the flip side, there's turbulence, which is to do with how much wind and air and temperature gradients there are, which can lead to more or less cooling. There was some work in the 90s saying maybe things were awry with the calculations being done so far. Let's see. Okay, so solar radiation. So this might be basic for a lot of you. I'll go through it anyway. So what happens to light when it hits a single ice grain? And we'll keep track of incoming light versus outgoing light. So if you imagine there's 10 watts per meter square hitting light, some of it gets reflected, a lot of it gets reflected. Ice is pretty reflective. Some of it gets transmitted, it's translucent, and then some of it gets absorbed. So if you look at our balance, we're in balance, which is good. And if you just look at absorption of ice, here's wavelength on this axis. And here's what our eyes see, red, green, blue. And then the other axis is this thing called the imaginary index of refraction, which just tells you how much light is being absorbed. It's on a log scale, more absorption, less absorption. So there's water ice. So it's very, very low in visible wavelengths. And also the lowest in the blue, more in the red and green. And that's actually why pure ice with nothing in it, if you have enough of it, is blue, because it's absorbing the red and the green more. But Mars is a dusty place. So this is the InSight lander, 1 year after it landed. Here there's no dust, and then suddenly everything escaped with dust. I never understand why they don't like take wipers. The mission actually ended after the sunlight couldn't get through because there's so much dust. But anyway, okay, so dust, if you remember, ice was here in the visible wavelengths. Dust is over there, but many orders of magnitude more absorbing. And it's the opposite. It's actually absorbing the most in the blue and the green and the least in the red. So that's why dust is kind of reddish. So there's just to compare them. Dust is many orders of magnitude more absorbing, which means it can darken ice disproportionately. And also that's why dust is opaque, ice is translucent. And what this leads to is this albedo. I'm wearing a white shirt today, so I'm reflecting a lot of light when I'm in the sun. If I wear a dark shirt, absorbing it. And yeah, which leads to temperature differences. And in math form, albedo is just the reflected light over incoming. So 8/10 or 0.8 in this case. So what we did with Steve Warren, who's an ESS and atmospheric scientist, we never actually met. And I contacted him during the pandemic and we wrote this paper together with my advisor, Phil Christensen at ASU. And yeah, essentially we wanted to see what does the albedo of snow look like when you add dust to it on Mars, because Mars is a dusty place, like we said. So pure snow, there's blue, green, red. It would kind of look like that. It's very highly reflecting when it's pure in the visible wavelength. Pure dust is that color. I was kind of surprised by how brown it was, but then I looked at an image on the rover and it was consistent. Now what happens if you mix them? So notice there's a small drop everywhere else is the same. When we add 10 to the -4%, almost nothing. Now suddenly the colors change as you add more and more. You go to 0.1% dust, and it's that brown color, and you could be walking by, see something and think, oh, it's dirt, but it's actually just snow with 0.1% dust. And it's all because dust is strongly absorbing, many orders of magnitude more absorbing. Just like on Earth, when you see snow and then a few days later it's black, if you actually took it home and melted it, the amount of dirt would be something like 1% or less. Because carbon is often from pollution or even dust. They both are strongly absorbing compared to ice. Okay, then the other thing is how big the grains are. So snow grains get larger over time, generally, and as they get larger, the chance of being absorbed increases. In other words, you get darker. So snow goes into glacier ice eventually. In between, it turns into this thing called firn. And what's happening is snow is actually mostly air. And as you squish it, the air is reducing. And then as you keep going, then finally the air gets trapped in the form of bubbles, which is glacier ice. And essentially the grains are getting larger, which increases the chance of being absorbed, so you get darker, and these I'll just step through. Essentially, you're going from snow on top, the blue line, to the purple solid line, and as you're getting larger and larger grain, you're getting darker. So a model is not to be trusted until you actually test it with real data. Luckily, we have points on Mars, one place where they made measurements. So of the ice and the nearby soil. And so we found that if you just had pure snow on the black line, you couldn't match the measurements of pure ice at all. But if you had a tiny amount of dust, 0.01%, you could match it. And the nearby stuff was matched by pure dust alone. So that gave us confidence. And then also there are these interesting measurements in Greenland, where they measured how much light is there at different depths within the ice. And here's the suspect, the ice in question. There's sort of granular stuff, and this is glacier ice. And here's what they measure. So it's the amount of energy at different wavelengths versus wavelength at the surface. And then below the surface, where the model is in the dash lines. And I'll keep going. And so basically, almost 77 centimeters down, there's still a bunch of light, which is not surprising. Ice is translucent. And the model was pretty good. Some people don't actually do the calculations at every wavelength. This can give you a lot of errors. If you just assume one value, a broadband value. If you look at the 12 centimeter curve, the blue line. So compared to the blue to this solid line, you would be in this much error at this wavelength and that much error there. So we wanted to compare that. And if you're trying to figure out if there's enough energy below the surface, you need to do it at different wavelengths to ensure you're actually getting the amount of energy right. And then just kind of in summary, currently a lot of Mars ice models just assume one broadband value again for albedo, but there's all this variation, which is very important to account for if you're trying to see if there's enough energy. Okay, now I've spoken enough. A quick question for you. Why is water in a glass transparent? But if there's the same water on top of white sand and it looks blue, and also if there's water on top of white ice, it looks blue.
Really scattered.
Okay, Rayleigh scattering. Any other? We sort of alluded to it earlier also.
Like the wavelengths or, well, no, never mind.
Yes, it is. It's everything's wavelength.
Well, I guess my thought was, but it doesn't make sense. It's like the sun is a different light than inside, but you have a glass of water outside, it's not blue.
Okay.
I don't think that's right.
Hope on Zoom says refraction.
That's also like a catch-all kind of answer. Yeah, it's basically how much water there is. When in a glass of water, you don't have enough. So I found a fund. And again, colors are distorted, unfortunately, but it's more clear. Here on my screen, this is white. If you just imagine, it's shallower here. So as less water, basically water is filtering out red and green if you have enough of it. But if you don't have enough of it, then it still looks white. So light's gone through the water. Some of it's been filtered out in red and green. Blue is left behind. It hits a white surface below and reflects back the mainly blue, and now it's gone through water again, filtered out red and green and come out. But this is so less water that it still looks whitish. As you get deeper and deeper, it looks blue. So if you took a glass of water and you filled up this room with just water and then you looked at it, it would look more blue. And you kept going as it gets deeper, then you're going to absorb more of the red and green essentially. Yeah, so there, you're just absorbing more in red and green. Rayleigh scattering, there was a paper in 1907 or something by C.V. Raman, who won the Nobel Prize in physics, and he thought ice was blue because of Rayleigh scattering, but it turns out he's wrong. And at the molecular level, he's right, but you never actually get to that level because ice always has scattering and stuff. And ice itself inherently is blue when you have enough of it.
What do you mean because it's not a single molecule? What do you mean?
Yeah, yes, yeah.
Okay.
Yeah, as, and for a bulk medium. Okay, so then, the other thing we'll look at is absorption. So what happens to light when it gets absorbed? It gets re-emitted in the thermal at these temperatures. And so here are the properties, absorption, essentially. Ice and dust is strongly absorbing at these thermal infrared wavelengths. Phoenix is very hot. Also what snake eyes see in these wavelengths. So ice and dust, in contrast to the visible, are strongly absorbing. What can happen then is the solid sort of greenhouse effect, where sunlight goes in, heats on the inside, and because ice is translucent, and if we just zoom into the top sort of area, look at the top few grains. Again, sunlight goes in, if you just imagine 3 grains, the last grain absorbs that sunlight, emits in the thermal, but ice is strongly absorbing the thermal, and essentially you're trapping that energy inside the ice, just like CO2 gas is transparent in the visible, but it absorbs in the thermal. So you have this sort of greenhouse effect. And this isn't fictional, we've seen it. So this is the drowning moth area in Antarctica, where they're walking along and everything was frozen. And then they noticed, wait a minute, there's actually liquid below the surface, even though it's frozen at the top. And so use the chainsaw to actually expose the liquid underneath. And they actually measure the temperatures as well. So here's temperatures in centigrade. Here's the melting temperature. And they noticed at the surface, it was cold, it was -3, but then 25 centimeters down, it was melting, and it was isothermal, the same temperature for up to a meter. And so it's that scenario we propose where there's ice, liquid water, and ice. And this can lead to maybe photosynthesis, is what we proposed in a paper last year, where if you imagine those mantles, those buried glaciers, in cross section, this is the crappy cartoon I made in paint or something, but it's just rock and then dusty ice covered with dust. And we're seeing patches get exposed. And maybe what can happen based on seeing similar cryoconite holes on Earth, which I'll show you. Maybe sunlight can go in, heat, and melt the ice below the surface, where it's also protected from harmful UV radiation. And you could have microbes that then come alive. The biology part, I'm hopeful people here can help refine. But yeah, maybe they come alive in the summer and then they go dormant in the winter, where everything freezes up. And the same thing happens on Earth, where these cryoconite holes. So here's a fun video that may play. I can find a mouse. Maybe you can see them. Oh, here it is. Yeah. So a guy actually stuck a camera into one of these holes. And they're frozen at the top. And then there's liquid inside. And there are these dark sediments that actually, that's how they form. There's dark sediment at the top, it heats up, melts into the ice. And then eventually a lid forms because it freezes. And sunlight goes in, and there's cyanobacteria and algae that thrive in the summer. In the winter, everything freezes and they go dormant, and then this restarts again in the next summer.
It restarts again, but in the dirt, I mean, the blood. How does it restart if it's submerged then? I mean, doesn't it have to start on the surface and then drop down or not? Maybe
So when it ends, the configuration is, if you imagine a hole, and at the bottom of the hole, there's the dark sediment. On top of it, there's liquid that froze into solid ice,
So now
and there's a lid.
Yeah.
And the lid stays, but then the liquid melts on the inside.
It's fine.
Because at some point, as the sediment is sinking into the ice, it gets to equilibrium where it can no longer sink any further. And that's the sort of stable configuration. And yeah, so we essentially modeled how much light would go into clean ice versus dusty ice. And this is actinic flux, which is how much energy there's in total at UV wavelengths, which is harmful, and then photosynthetically active radiation, which is good, obviously. And there's the actinic flux. And to no surprise, since ice is weakly absorbing in the blue, you can get, this is then 700 centimeters, so 7 meters, you can get blue light going all the way down to 3 meters. But so does harmful UV up to 2 meters, but in between, the UV is blocked, but you still have photosynthetic light, so you're in a happy sort of zone where you've blocked off the harmful radiation, but still have the helpful radiation. But as you add more dust, this shrinks rapidly. So you go to 0.1% dust, you're now at 6 centimeters from 4 meters. But still, on a centimeter scale, between, let's say, 2 centimeters and 5 centimeters, you have a safe zone. And essentially, we did this for a bunch of dust contents, finding the green areas are kind of where you're in a good place. So if it's very clean, you would be in a relatively habitable zone on the order of meters. As you get more dust, it's on the order of centimeters. And we did this also as the snow grains get larger and larger. Yeah. And essentially they're these relatively habitable zones, centimeters to meters into ice on Mars. Today, we were talking about ice before, and whether it's habitable today or in the past. So now the one other sort of diversion or part of this is looking at the turbulence, which I'll go into quickly. And again, background overview, airflow can be smooth or rough depending on how it's flowing. So if there's stuff in the way, it can transition from smooth to rough due to friction or shear. And it's how rough these or how large the things at the surface are that dictate that. Also, here's some cigarette smoke. As it goes higher and higher, it can no longer sustain itself at some length, after which it gets turbulent. And this is just due to buoyancy, which on Mars is particularly important because water vapor is much lighter than the gas on Mars, which is CO2. So CO2's molecular weight is 44 and water is much lighter. So any molecules want to just rise up buoyantly, which enhances turbulence. All of this is happening in the area we live in, called the atmospheric surface layer, which is the lowest 10% of the full boundary layer. That's where the helicopter used to be. And yeah, things are dictated by this roughness. And what we did is we took a 1D model and essentially applied it to Earth, Mars, Titan, and exoplanets. And it's ready for use and for all these situations. I won't get into the equations today. But yeah, the nice thing is it can be used on any body with an atmosphere. So, and we did test it with the limited data available from Earth, and then Mars, Titan. Yeah. So here are some examples. So this is an ice covered area on Earth called Lake Hoare. And it's really thick. It's like a few meters of ice that freeze over this lake. And we compared what people use generally for Mars. So this is the measured versus the model. If they agreed perfectly, they would be along that line. We found what the current state of the art that people use for Mars was over predicting the amount of ice loss. Which again means you're taking away energy that might be available for melting. So why is this happening? Here's another video that's also short. And you might see this in the desert. I don't know if Spokane or Spokane is hot enough, but Arizona, it definitely is. What happens is you go out there and there's no wind, and then suddenly a gust of wind will hit you, and then nothing, and another gust of wind will hit you from a different direction. And that's due to buoyancy. So the surface is getting hot. And this is a big container with water and then aluminum pellets, so you can see. And then what's happening is, and a heating rod. As buoyant fluids rise, they go up to the top of the boundary layer, which on Mars is like 10 kilometers. They cool down and then they sink back down and come back in these drafts that are like wind, but not exactly. They're these random sort of gusts. And it's buoyancy that's causing this instability. Enhanced on Mars because water is lighter than CO2. And what's up again, narrow buoyancy driven updrafts that come back down. And you can feel them, but as they change direction. And quickly how high are they? They are as high as the boundary layer. And their velocity depends on a bunch of things, the roughness, the buoyancy, and how high they are. But remember that famous paper in Science? So we looked at the equation that was central to that conclusion, and it has a bunch of things. But it turns out where it came from was a textbook in the 20s for buoyancy over heated plate. So it only accounts
for buoyancy, it doesn't account for how rough the surface is or how high the boundary layer is. And so, which are crucial for this buoyancy driven process that happens on Mars a lot. So we wanted to just compare how much energy do you lose according to that equation versus sort of the update. And so this is energy loss. And loss means you're losing energy that could be used for melting. That's why it's important versus atmospheric pressure. So, and some history, Ingersoll did it, and then Shane Byrne was Ingersoll's student, and then Dundas was Byrne's student. So they redid his equation, and 40 years later, got a similar answer. And then this is our result. It depends on how gusty this atmosphere is, which is something you can measure. So that's very gusty, very rough surface, less gusty, smoother surface. Essentially, there's this 2x variation for this imaginary case where everything is at the melting temperature, the atmosphere and the surface. And essentially, yeah, you can have greater or lesser cooling or heating depending on the local conditions. And what's next is what I'm working on right now, is putting these pieces together into this energy balance model. It was funded, but the problem is the funds haven't been sent yet. So I had to have my salary yesterday to 50%. I have 2 months of salary left through internal funding, because this is my main funding and it's not here. So it's a crisis actually. But what we're doing is there's this really cool model that Rachel Jordan made, and she is so this is during the Cold War. They were trying to see if could you tell the difference between a tank track and undisturbed snow from space or from aircraft. And so she made this thermal model that has all these processes of liquid water flow and refreezing, things like that, for CREL, the Coal Research Lab in the Army. And we are now improving it 30 years later with her help, and Steve Warren and Gary Flo Christensen, to incorporate these processes first for the Earth, improve ice and snow modeling on the Earth, and then later apply it to Mars once we know it works on Earth. And these are some, preliminary results. I don't know if you should focus too much on them, but these are the same temperatures measured at the place where the subsurface melting. Those are the red. The purple lines are our previous model, and then the black is our current model. Again, don't have to go into it. And then just to summarize, small amounts of dust and also how large the grains get can lead to 10 times more heating when you account for it. And then sunlight can go through ice because ice is translucent and actually heat and form liquid water inside the ice. Not that deep, 25 centimeters to a meter, because below that there's no sunlight going in for most cases. And then accounting for these turbulent conditions can lead to more or less cooling. And that's it. And thank you to lots of people, Steve, Phil, Gary, Rachel, and I'll be happy to take questions.
You know what ice bridges or snow bridges are?
Maybe.
I've like seen this before, like if you're like later in the season up on a mountain, you get these like bridges of snow over rock, and there's like a gap between the snow and the rock. I was wondering if that's the same process you were talking about with the cryonite holes. Because like it melts from like the bottom up, if that makes sense.
Maybe a little bit. What's happening in the cryonite hole is that if you have ice at the surface and you have these dark sediments, which could be rock or something else, then here's the ice at the surface, there's some sediments, the sunlight heats them, and then they start melting around, and then they gradually start sinking. And then what happens at the end is there's sediment inside a hole. And so you walk by and you see a hole, and there's dark sediment at the bottom. And what's happening throughout as it's sinking deeper and deeper until there's a point where the sunlight is not going further. So it's now in equilibrium. And then there's liquid all around here. And then usually there's some gap when it freezes. So when it freezes, it looks like this, where there's an ice lid, and then there's some liquid maybe in between, and then there's some gap for some air, and this is where the bacteria and stuff go. Okay.
Looks like seems like a different process.
Maybe a different, yeah.
Super interesting first, thank you for the talk. It looked like you were considering just sort of predominantly the plant chlorophyll peak as your basis for what photosynthetically active radiation would look like. But in lots of stuff that isn't plants, that wavelength is shifted. You know, in the ocean, there's you see lots of different configurations depending on which cyanobacteria you're looking at, et cetera. And there's lots of other sort of accessory pigments that you could imagine being stronger. Have you considered looking at what that sort of radiative, I can't remember what you called it, but the like radiative habitability looks like at a different wavelength for PAR?
Yeah, so. Maybe I'm getting confused, but we essentially looked at the whole range,
Okay,
not at one value.
Okay.
Because you're saying, like you're saying, there may be different organisms that favor different
yeah.
peaks. Yeah, so we weren't isolating one wavelength. It was
Okay.
just the whole range.
I was just in the next one, when you look at
This
the
one,
dusty condition,
here,
like there's way more in the red and it goes down quite deep into it, right? So you can imagine an organism with predominantly red pigments might be able to live much further down in that.
yeah, and I think there's work that could and should be done in trying to refine what kind of bacteria would favor Martian conditions where the dust is shifting the peaks. Yeah, and I'm open to working with people, and also at APL, Karin Younga and Aaron Firth and Bonnie Light and I are discussing trying to recreate the scenario. Not almost like this, trying to make a fake cryogenic hole with Martian dust simulant and actually putting cyanobacteria in them to see how long they would survive. But yeah, we're open to working together.
So great talk. One of your results being, right, that the gustiness at the surface boundary can really drastically affect how much energy is being lost. So I'm curious about, like, compared to Mars, what's the kind of like time variation on that? Like, do you know, on scales of like days, is it changing from twice as much energy loss to half as much energy loss? And also, how is that affecting the potential for this ice to be melted underneath the surface?
Yeah, so the time would change, throughout the day, the temperatures of the air, the surface and the wind will all change depending on where you are. And so what we have not done yet is currently we're applying the ice melting model on Earth first and we're testing extensively where there are measurements. Because on Mars, once you switch to Mars, unfortunately, people who've modeled ice on Mars so far have not bothered to check if their model works on Earth, which is easy to do. So we don't know if their results are right or not. And then, so what we're trying to do is at least test it on Earth first. And so we're in that stage. But yeah, you can imagine maybe cases where if they're small ice patches, then the overall air around is dictated by what's not ice, which is dirt, essentially. And so in those cases, you can have cases where the air above the ice is coming from land that's nearby, that's hot. And in that case, the atmosphere can become stable, which means the surface is cold, but the air on top is warm, which actually inhibits turbulence. And in that case, the energy losses are low. So that's possible. But yeah, there could be a bunch of scenarios that inhibit or are better for melting that we will explore.
Okay, so maybe a far-reaching question, but in that case, like, would you be able to like discern if there were like more favorable geologic features that you'd want to be looking for ice pockets?
Yeah, well, we definitely think like the gullies where these ice, I think those are the features. And as to where in our proposal, we propose to analyze a bunch of these exposures to make almost like a probability map of here are the places we should go because based on, yeah.
Cool.
But you had a second part of your question. What was it originally?
The,
Something to do with wind and then,
I think you answered it pretty thoroughly. Yeah, thank you.
Hi, I have a questions about the coupling between turbulence and dust emissions and potential impacts on energy balance. I think if you look at turbulence, what it does to the surface layer in a dusty environment is when you have some wind, like you can lift off quite a bit of dust on this surface, right? Like, and turbulence also, control dust emissions. And also like how much dust that can suspend in the air. Do you think that can have a significant impact on the energy balance in your system? And if so, like, is there some way to model it? Because this is a pretty tricky problem even for Earth model as well, like how you model dust in a turbulent environment.
yeah, there have been some papers in the last few years taking the weather WRF, whatever it stands for, some weather or something forecast.
Yeah.
That model for, and there's a Mars version. And the last few papers have been about trying to figure out how to parameterize how dust is being lifted, like you're saying. And then once it's in the atmosphere, if there's too much of it, it can block the sunlight and then heat locally, and then things can happen. Or if there's not enough, it can absorb thermal radiation from the surface up. So we're not getting into all of that because there's so much unknown right now. Yeah, but it could be that there are random gusts that these areas are not that dusty. There's dust all over, of course. The ice itself is, well, if you can see it, there's less than 1% dust in it. Because greater than 1%, it would just look like dust alone. So yeah, how much of a role it would play is not known and may not be that high. But also it's not known.
Okay.
Yeah.
So the idea is because you're targeting like cleaner environments on Earth, sorry, on Mars, that you can actually see the ISO that way.
Yeah, because once it gets too dusty, there's no sunlight penetrating the surface also, in which case there's no melting below the surface or anything.
Okay.
So, yeah, and also we wouldn't be able to detect it from orbit in the first place, which is all we have right now. Yeah, if there are any other questions or views you want to send me, I have my email. Also, if you have ideas on what to do with this, everyone's stuck in the funding situation, but yeah.
Do you have some updates, like how bad is it, the funding situation?